talk to you about something which is not directly connected with Ruby, but the presentation will also feature some Ruby details. So what I want to talk to you about is algorithm, and I call this talk Beyond the Language. You will understand why during the presentation. So I want to start the talk with a problem, with showing you a problem. Just a little bit of background. This talk was originally designed to be scheduled after the coffee break. So that's why I mentioned the beignet. But all of you had breakfast this morning, probably, so I think that we can also keep the beignet here. Maybe it was croissant, but that's fine. Okay, so we have a problem today. And the problem we want to solve is there's a coffee table with a lot of beignet. Yummy. Of course, you're really greedy, so you want to eat some beignet. Actually, you want to eat as much as beignet you can. But unfortunately, there's a mean guy here around who put some poison in one of the beignet. And because of the poison, the beignet weighs a little bit more than the others. So let's pretend that all the other beignet has the same weight. The only way for you to understand what is the poison beignet is to weigh them, either with your hands or with a scale. Because of the poison, yeah, of course. And each time, so the constraint is that each time you weigh the beignet, you waste time. Of course, it takes time to take the scale, try that, yeah, it's good, no, it's not good, blah, blah, blah. Okay, so what's your goal? The goal is that you want a way to eat as much as beignet as you can, and of course, ideally without eating the poison beignet, unless you're really accustomed to that. And before all the good beignet are gone, because there's a lot of greedy people here in the room. And so what you really want in reality is an algorithm that will tell you what is the poison beignet in a fast and efficient way. So I'll leave the question here for a second, just start thinking about that. I quick introduce myself. My name is Simone. You can find me with a handler webpost pretty much everywhere, GitHub, Twitter, and so on. I work for DN Simple. Now, quick question, how many of you installed Gem? Okay, awesome. So that means you use our service. So we provide DNS, hosting, and domain registration, SSL certificates for a bunch of different services and cool people like RubyGems, like Atom, the GitHub editor, and Travis, and so on. I have several interests. According to this conference page, the interest includes diving, sharks, and algorithm. Now, I've been raised and born here close to Turin, and I know that sharks and diving are not really appropriate for Piedmont, so I will talk about algorithm. It is worth to start defining what is an algorithm. Now, one of the definitions of algorithm is a process, or even better, that's what I like, a set of rules to be followed in calculation or other problem-solving operation, especially by a computer. So there's a close connection between algorithm and computer, yeah, of course. There's also another different definition, which is a word used by programmers when they don't want to explain what they did. So how did you solve that? Yeah, it's a complex algorithm. You wouldn't be able to understand that. So yeah, don't bother. It's important to understand that an algorithm is not strictly a problem. Okay, a program. In fact, a problem can be viewed as an elaborate algorithm, okay? So generally we have that computer programs contain several algorithms that details the specific instruction a computer should perform in order to execute a specific task. And here comes back the definition of set of instructions, set of tasks. So what we can say, in fact, is as a programmer, you use a programming language, whatever you like, to implement algorithm in order to write program. So that comes to that specific question I saw almost 1 year ago on programmer.stockexchange, which is a sister project, a sister site of the more famous Stack Overflow website. And there was an interesting question. So the interesting question is, do I need to understand algorithm and data structure in order to be called a programmer? So I don't want to answer the question right now. Actually, I don't really want to answer the question. I will do it at the end. But I want you to start thinking about that. And in fact, the whole purpose of this talk is to help you to start thinking about discovering and learning and studying algorithm. So let's go back to our original problem, the testy Binet program. Quick recap, we have a coffee table, we have a Binet, one Binet has a problem, there's some poison, so it's more heavy, so I want to find the one which is more heavy. And, but I have a problem that every time I perform the operation, I have a cost, and I waste time, and I want to eat as much as Binet as I can. Again, ideally without die. So the next step is to try to formalize the algorithm. Okay, so that's probably one of the most challenging tasks in solving a problem. In fact, sometimes even more challenging than solving the problem itself. So trying to formalize the real-world problem into a mathematical model or a more formalized model. I did that for you today. So the problem is find the heaviest item among n items in a collection. The instance of the problem is a number of items, including, of course, the item we want to find. And the computation model for today is the scale. It's a very simple computation model. You can even use your hands. Each weight taken, so each weight action takes a fixed cost. And our algorithm is, of course, the weighting strategy. And the goal is that we want to have an algorithm that finds the heaviest item in the collection. The algorithm should be, of course, correct and ideally efficient. Okay? All good so far? Okay, good, awesome. So let's try to find the simplest algorithm. I want to know what's the simplest way to do that. Now, if you are older than 30 years old, you probably remember the Kinder surprises and the small figures inside the Kinder. So what all the young kids, including myself when I was young, was used to do was to take one. So they wanted to know, we wanted to find the best surprise. And so we were just taking the first and trying to weight all the other and shake all the other to find the best surprise. And that's actually the most simplest algorithm we can find. So the simplest algorithm just takes the first item and compare all the other items with the first one, okay? Easy peasy. So we have our Binet here, we take the first, and we start comparing with the second. First step. Second step with the third, fourth, fifth, sixth, seventh. Yay, we found the poison Binet. Well, of course, don't try to cheat. The Binet are all the same. They are not black, otherwise it would be too easy, but I did that just for you. So hey, we found our Binet, and we had 8 Binet in our collection, and it took 6 steps to find the poison one, which was in position number 7. Now, that's an important thing to keep in mind. Every time we talk about algorithm and we measure the algorithm, we always consider the worst case scenario, which means we don't really care whether the Binet is in this position or this position or this position. What we do is that we pretend the position to be always the same or the algorithm to cost the worst scenario, the one where we have to maximize the computation of the algorithm, okay? So, is the algorithm correct? Raise your hand if you say yes. Okay, raise your hand if you say no. Come on. Okay, so it's correct. Is it efficient? So, that's challenging. Raise your hand if you say yes. Wow. Raise your hand if you say no. Awesome, we have a lot of engineers here. Okay, in reality, the answer is, what? I mean, I didn't even explain what efficiency means. So in reality, what we have to do now is to talk about cost of the algorithm. What does it mean that an algorithm is efficient, okay? So we have a measure to to measure the cost of the algorithm, the complexity of the algorithm. But for now, for simplicity, I will define the cost of an algorithm as an estimation of the resources needed by an algorithm to solve a specific or the specific computation problem, okay? So resources can be whatever. It can be CPU, can be processing time, can be storage. So let's suppose you have to sort a lot of records. You might find a problem, which is a storage problem. But for most of the time, the constraint is the processing time, the CPU time. Of course, the lower the cost, the higher is the efficiency of the algorithm. In computer science, we have one way to label the cost of an algorithm, which is called the big O notation. So the big O notation is used to classify the cost of an algorithm relative to change in input size. Okay, so that's a very important thing we'll see in a second. It's important to keep in mind that in mathematical, this is called an asymptotic notation, and I will explain what does it mean in a second. So for now, keep in mind it's an approximation. That's the human term you can use. So the big O notation is a way to measure the complexity of the algorithm in the worst case scenario, as I explained before. And yeah, unfortunately, we need a little bit of math in order to understand the complexity of an algorithm, but don't worry, I try to keep things simple for you. So what I'm showing you here is a list of the most common cost for an algorithm, and at the top you can see the number of items in input. So we have 2 items, 10 items, 20 items. Now the numbers you see in the body of the table, assuming a very simple mathematical model, which is, I don't know, the cost is 1 something, let's say 1 second, you see how the type of notation perform, how the function perform depending on the input size. So for example, we have the constant one, which is called O1, that always perform in constant time. I don't really care how many items I have, it will always perform in constant time, which is probably the most interesting. Then we have the linear that grows with the number of items in your input size. Then we have the logarithmic scale, and as you can see, when we have 10 items, it takes 3.3 something, and when we have 20 items, it takes 4.3 something. So it increases, but really, really, really slow. Then we have the quadratic, of course, two items in the input means 4 units, then 100 units and 400 units. And now you can see the exponential, which is one of the most terrible label to see in your algorithm, because it means your algorithm will take ages to complete. Here you can see a chart that pictures, that draws, plots the increasing curve of execution time of an algorithm depending on the input size. So we have elements on the x-axis, we have operations, number of operations on the y-axis, and you can see the increasing. And now the interesting part, I won't go into the details, but the interesting part, as you can see, is that the O notation, being an asymptotic notation, allows us to compose the complexity of an algorithm. So we have, in some cases, n log n, which is the typical complexity of a sorting algorithm. Then we might have log n, for example, but being an asymptotic notation means that we ignore the multiplicative constant, okay? And I'll explain that a little bit more in 1 second. So just keep this picture in mind. That's all I have to ask you to remember about math for today, so you'll probably be really lucky. Let's analyze the cost of the first algorithm. So we call the first algorithm 1 versus all. Again, we take the first one and we compare to all the others in the collection. We say that the first algorithm is correct. Now, what's the cost of the first algorithm? Linear, cool, okay, it's linear. And so the cost is n, and the big O notation is O the n. Is it efficient? Well, it depends. It depends on what? How do you measure? How do you explain efficiency? So now, generally you say that an algorithm is efficient whenever it suits to you, but even better, whenever there is no faster algorithm to solve that, or the complexity of the faster algorithm doesn't really work for you, okay? So in this case, is it efficient? Well, not really. In fact, we can have a different algorithm. Now, another algorithm we can use is to compare pair of items one by one, okay? So we have our bignè, we compare the first two items together, first step. The second two items together, the third items together, and the fourth pair of items together, okay? So notice that it took 4 times, okay, to solve the problem, and we found the solution. Now, is it correct? Cool. How much does it cost? Okay, so the cost of the algorithm, technically speaking, is half n. Okay, it's half the time of the input size. But in terms of big O notation, it's always n. Okay, so technically speaking, the previous and this algorithm, in the big scheme of picture, are essentially the same in terms of performance. That's because, as I mentioned, we ignore in the big O notation the multiplicative constant, and half n means n multiplied by half, okay, which is a constant. So in the big O notation, in is n. Of course, if you have to choose which one you might want to use, you probably will use the second, because it will slightly be faster. But we'll see in a second that it's not really that fast compared to other solutions. So is it efficient? Good. It depends. Depends on what? Well, do we have a third algorithm? Of course we do, otherwise my talk will be finished here. So we have a third algorithm that I call divide et pesa. Okay, so we split the collection of items in 2 groups, 2 sets, ideally of the same size. Now there is an explanation of what you do when you have odd items. You weigh them, and you eat the one collection which is the lightest one, because clearly the poison one is not there. So you keep the heaviest one, and you keep iterating. Okay, so you split that again into sets, and you keep doing over and over. This is an example. So we split into sets. Okay, one will be the heaviest one. So we discard the other, and we weigh them again. Okay, let's move on. We discard the first part, and here we go. We found the poison bignè. And that's in the, it took 3 steps, okay, to find the solution. And the input size is the same of the previous one. Is it correct? Of course, I showed a picture. What's the cost? So here the cost is logarithmic scale of 2. And I'm not going into the details. If you're interested in learning more, I can explain that to you, but it will take a little bit more mathematical explanation. But the cost in terms of big O notation is log of n. Okay, that's the label we use for the third algorithm. Is it efficient? Okay. The right answer is depends. Depends on what? Well, it depends on the fact that you might be surprised we have a 4th algorithm. And the 4th algorithm is a little bit more clever than the 3rd one. What the 4th does is that you split the collection in 3 groups this time, okay? You weight only 2 of them, the one with the equal number of items. And if they have the same weight, well, clearly the poison one is not there. So you can discard both, and you keep the 3rd. If one of them is heaviest, that means that the poison one is there. And so you discard one of the ones you are weighting and the 3rd one. Here we go. So 3 groups, first, second, and 3rd. Again, there's a possibility to deal with the odd number. And hey, they have the same weight. So clearly, the poison one is not there. So I can eat all of them, yummy. And here we go. I found the solution. Of course, here we still have 3 groups, but because the number of items were just 2, the 3rd set will be empty. Is it correct? Yes. What's the cost of this algorithm? Excellent. So if we talk about the big O notation, the cost of the algorithm is exactly the same of the previous one. It's still logarithmic scale, but practically speaking, it's logarithmic in base 3. So it's slightly more fast than the previous one. Is it efficient? Yes, it is. There's no way to do better, and you can demonstrate that, but I'm not going to do that. So just to give you an idea, that's the speed of our 4 algorithms. If we consider 1 minute to wait, it's for each wait action, okay? So as you can see, between the first and the second, there's not really huge difference compared to the third and the fourth. So that's the reason why, generally speaking, the big O notation is okay, is affordable. So we don't really care even if the second algorithm was half the size in the big scheme of picture. Because if we have 10,000 elements, the third algorithm will take 13 minutes compared to 3.5 days of the second one and 6 days of the first one, okay? So it's a lot of time if you have a huge coffee break table, okay? It will take a lot of time for you. Now, what I want you to start thinking about in terms of performance is the idea of language, programming language versus algorithm, okay? So more and more, I've been in the Ruby community for more than 10 years, and especially at the very beginning, it was like Ruby 1.8.6. It was easy to hear about people complaining about the speed of Ruby. So Ruby is slow and so on. And at that time, it was probably true. Now, the thing is that very often I hear people complaining about the performance of a specific language, but they don't really blame themselves. They pretend that the problem is the programming language, whereas the problem can be a bad designed algorithm. Okay, so that's something that you have to start thinking in mind. So should I simply use a faster language? So I wanted to show you, but I didn't have the time, that the same Fibonacci algorithm, the standard one designed in Ruby, implemented in Go, is still slower than a Fibonacci algorithm written in Ruby using the dynamic programming technique you can use in algorithm, okay? So in that specific case, changing the language even to a faster one didn't change anything. Exactly how, in that specific case, the time will be irrelevant. I mean, 6.5 against 13, it's nothing, okay? So let's move forward, and I want to quickly talk about data structures, because data structures generally go along with algorithm. And in order to keep the talk more relevant with Ruby, I want to talk about data structures specific data structures in the Ruby virtual machine, which is called the hash table. So nothing fancy here. We have a hash, we set some values, we delete some items, and we look up some items, okay? That's how you interact with the hash table at the high level when you create a hash, okay? But in reality, behind the scenes, the hash table is used in several different places in the Ruby virtual machine to store mostly any state behind the scenes of your Ruby program, okay? So in an ideal world, all the 3 operations I mentioned before should cost constant time, okay? That would be awesome. Let's try to do that. So let's try to find a possible approach. So one of the approaches could be a linked list, okay? So we have a bucket where we store the first item of the hash, and then we link that to the second one, and we link that to the third one, okay? So what's the problem here of this solution? Can you spot that? Is it efficient? No, okay, why it's not efficient? It's not because the search is constant time. Sorry, it's linear time. It means that if you have 1,000 items in your hash, it would be freaking slow, okay? And in fact, that's not what's happening in Ruby. Now, if you see, if I have a hash table with 64 elements, it takes 0.003 seconds to perform 10,000 lookups. And it's the same, mostly the same for 32,000 items in the hash. So it's essentially almost constant time. Okay, so how they do that? So what happens is that you have the way Ruby stores this information is by using an array of buckets. So that's an array, and by default, the virtual machine starts with an array of 16 buckets, 16 items. Whenever you set a specific item to a hash, what happens is that the key is passed to a very special algorithm. Again, that's another algorithm interacting with algorithms, which is a hashing algorithm. Okay, so the hashing algorithm computes a specific representation in integer of that key. And you can access the number, so the value of the hash, using the .hash method in Ruby, okay? Once you have that specific representation, which is more or less the same of a git show, okay, what you do is you compute the module of, by 16, which is the number of buckets you have, and you get 4, okay? So what do you do with this number? Well, you start a linked list, leaving the pointer to the 4th, actually the 5th, because arrays are indexed from 0, of the storage table, okay? And now you can see the pattern. When I create a new key, I do the same process. I compute the hash, I take the module, the modulo, and I use the index key in order to start attaching more and more entries to my bucket array. And I do that over and over. So when I have another key where the final digit is the same, well, I just attach that to the previous one, and I keep going on, okay? I keep going on, and the storage increases to the point where I reach what it's called the maximum density. So Ruby virtual machine keeps track of the density of a storage table, and density is essentially the number of items in the linked list starting from a specific bucket in the storage array, okay? So when there's a constant in the C code of a virtual machine which says when the number approaches 5, then do something. What will happen is that the virtual machine will increase the size of the bucket array. Here I just demonstrated by 1, but actually we'll do that larger than 1, just to optimize performance. And as you can imagine, we'll recompute, rehash all the keys of the previous stored items. And the effect of that is that you will decrease the density of the storage. Okay, so all the linked lists now have a density lower than 5, which was the maximum number of items. Okay, so now you can probably start thinking what happens here when you have to find a specific item in the hash and why the performance are so effective. So when you have to search an item with the key n, what happens is that the key, the value of the key is passed to the same hashing algorithm we used before to store the information. So we get the hash, we compute the module by the by the size of the storage array, and then we go straight to the position where we have the pointer, the linked list. Now, accessing an element in array is constant time because of the way the array is stored in memory. Okay, so we have constant lookup of the pointer of the linked list. And then, well, easy. We just loop over until we find the key. Okay, and because the number of items here is guaranteed to be a maximum 5, even the lookup, so looping 5 elements, is almost constant time. So the result of that is that the lookup, even in a huge table, is approximately constant time. Okay, so that's an example of a data structure along with an algorithm in order to increase and maintain performance. Of course, you can try by defining a very bad object. You can override the hash method, and you can mess up with your code pretty badly. So what I did here is that I forced the Ruby object to always return 3. So all the items I will create will be stored in the bucket number 3, okay? And of course, I run a benchmark, okay? So I run a benchmark by using a bad key and a good key. So I created several different arrays. That's the number of items in the collection. And as you can see, the time required to perform a lookup using the bad key, and for the first key, and I'll explain that in a second, increases with the increasing of the number of items in the collection, whereas for the good key, it doesn't increase at all, okay? Now, it's interesting and that's, of course, the graph. As you can see, this is the linear graph, and this is the constant graph. Now, it's interesting to see that the last key has always constant performance, okay? And I won't give you the answer here. What I want you to do is to tweet the answer, possibly just copy me in the answer so that I can read that. So I want you to think a little bit about that, about what I showed you before, how the virtual machine works, and see if you can find the reason why the last key has almost constant performance. Okay, so tweet that. I don't recall what's the hash for the conference, but you can use that. And please CC my Twitter handler. It's @Wapos. And so you won't win anything, but yeah, except like, congratulations. Okay, good. So let's go back to the original question. Do I need to understand algorithm and data structure to be called a programmer? Well, probably not to be called a programmer, but if you want to be called a good programmer or a great programmer or a real programmer, yeah, probably yes. You need to start thinking about designing your code and improving and learning some algorithm. And if you want to do that, that's an amazing book, the Algorithm Design book. And the other one, Ruby Under a Microscope, is a book probably a lot of you are already familiar with. That goes into the deep of the Ruby virtual machine. And so the last part of the talk uses some ideas from that. So unfortunately, it's a little bit old, but the idea behind are still good. Okay, so you can start from that, but of course, it will take you some exploration of the Ruby virtual machine, especially for the newer version. Most of the code is referencing 1.9. And I want to thank Luciano Gualà, who was my professor, algorithm professor at the University of Torre Vergata, because his passion was extremely inspiring for me, for this talk and in general to learn about algorithm and be a better programmer. And Pod, which is the author of Ruby Under a Microscope. So thank you very much.